Welcome to another session of the Wireless Lab course, in which we will be investigating the effects of the RF front-end components on the communication signal. Specifically, we will be focusing on the amplifiers, oscillators, and the mixers, and we will be utilizing the components from the mini circuit company as shown on your screen. And it will be great if you can go through the data sheets of these components before coming to the lab, so that you can familiarize yourself with the operational frequencies and the biasing voltages. Before start implementing the first part, we will first do the parameter setup at the VSA and at the VSG as shown in the manual here. So let's go to the VSG. We need to set the frequency at 913 megahertz and transmit at the amplitude of -30. Okay. -30 dBm, and the modulation format will be, as usual, make sure you make the digital modulation on, and then go to the single carrier as usual. We set the modulation type to QPSK, which is already selected. We make sure the filter is root Nyquist with a alpha of 0.3. And the symbol rate should be 20 kilosymbols per second. So now we are all set, and we can allow the device to start transmitting by pushing the RF on button. And we can go to the receiver part now. We need to set the receiving frequency to 913. This is megahertz. To set, we can reduce this span to. So here is our signal. We can see it. So we are also required to observe these tools here. So let's go and do the setup as well. We will go to the demodulation mode as usual and set the digital demodulation parameters, the modulation format of QPSK, and the symbol rate is 20 kilohertz. The filter type rotary cosine and 0.3 alpha. That's it. So we need a grid of 2x3. The first plot we will put the spectrum. And here we'll put the EVM. Here we will put the polar diagram, and here I'm going to put the constellation diagram. In the last two figures, I'll put the eye diagrams as usual. This is going to be a QI diagram, and so the analysis tools are all set up, and we are required in the first part, in which we will be investigating the effect of low noise amplifier. In the first part, we need to record the transmission and reception without using the LNA itself. So we will save this. We will take a screenshot and save this layout here. But since we in the next part we are going to observe the gain of the low noise amplifier, so it's better to if we measure the power that we are receiving as well. So to do that, I'm going to show the power and show the occupied bandwidth. This is for the sake of comparison so that we can see the effect of the amplifier that we are using. So we are receiving around -80 we are transmitting at -30 dBm, if you remember, and we are receiving around -80 dBm. So we'll take a screenshot of this and you will do the comparison, with and without the amplifier in terms of EVM constellation, eye diagrams, and the bandwidth of the signal. And the received power of the signal, as well as the bandwidth of the signal, as we will see. So now let's move to the second part. Now we will stop the transmission and connect the LNA to the, as shown. Connect LNA to the system as shown in the figure here. The steps for implementing the circuit shown in the figure 1 outlined in the part B here, as you can see. In this case, we will need a DC power supply so that we can provide the biasing voltage to the LNA. And the biasing voltage is specified in the manual is 15 voltage. And as you can see on your screen, this is how I implemented it. And you will connect the output of the power supplier to the biasing pins of the LNA, as you can see on your screen. And the red one is the positive, and the black one is the ground. And the output of the VSG will be connected to the input of the LNA, as you can see here, and the output of the LNA will be connected to the transmitting antenna, as you can see on your screen. So by following these steps outlined on the part B, you can easily implement this part, and after this one we will be ready to transmit by using the LNA. And now we can start transmitting with the LNA connected to the VSG and observe the received signal. So as we can see at the VSA here, there are some clear improvement on the received signal quality in terms of the received power here, as you can see, compared to the previous one, the EVM, and the clarity of the constellation diagram. So you can save this one, and also we are required to repeat these procedures for different transmission power, like from -30 to -20 and then -10 dBm. So we will do that now. We will increase the transmission power, and we are supposed to do this for for each power with and without the LNA. So let's now transmit at amplitude of -20 dBm. I will first disconnect the LNA because we need to transmit with and without the LNA. So I have connected the antenna without the LNA, and let's observe what we are receiving now. So this is the received signal when we are transmitting at -20 dBm without the LNA. So you will again save this figure and then reconnect the LNA and see the difference. So now I have reconnected the LNA back to the VSG, and I will start retransmitting. So you can see at -20 with LNA, we start having some distortion at the received signal here, as you can see. We're having the intermodulation products. These are the third order intermodulation products that we are having, and this is because of as we increase the power, we are moving to the nonlinear range of the amplifier, which will cause the distortions like harmonics and the intermodulation products. So now when we are moving, we are working at the nonlinear range of the amplifier, we will be having harmonics as well. So as I said, this one that we are seeing here, the spectral regrowth, because of the third order intermodulation products. We can also see the second order, which will be in the next harmonic, which should be at 1826 megahertz. So you can see now here we are having another signal, which is a harmonic of the fundamental signal that we are transmitting, and this will cause the interference to other user who is working at this particular frequency. Yeah. So again, you will do this for the minus 10 dBm as well, in which you will observe the same thing. Maybe we can check the next frequency, which is 2739 megahertz. So you can see here also we are seeing receiving another signal here. So you will repeat this procedure for minus 10 dBm, and you will comment on the differences the differences when we are using and without using the LNA as you're supposed to do based on the. Now we need to introduce a filter to our circuit system so that we can suppress the harmonics that are being caused by the LNA. And to do this, I have chosen a filter of a bandwidth of 1000, a low-pass filter basically of the bandwidth of 1000 megahertz, so that the harmonics that are happening at 1800 something and the higher frequencies will be suppressed by this filter. And the filter is connected, as you can see on your screen, is connected between the LNA itself and the transmitter, so that the harmonics from the LNA will be suppressed prior to the transmissions, so that we don't cause any interference to the adjacent bands. So now let's transmit and see what we will be receiving at the receiver. So at the fundamental frequency, which is 913 megahertz, we will be receiving the signal as usual, because this one is not suppressed by the filter. But at the same time, the spectral regrowth caused by the filter will not be suppressed by this. Caused by the LNA, the spectral regrowth caused by the LNA will not be suppressed by this filter, because they are very close to our desired signal anyway. But if we go to the first harmonic, which is 1826 megahertz, we will see now we no longer have the harmonics here, because it has been suppressed by the filter. Similarly, for the next frequency, which was 2739 megahertz, also we have nothing because of the filter that we are using.